Good day, I'm Dr. T, and welcome to my whiteboard. So right now I'd like to show you how we represent molecules more than just their empirical or molecular formulas, but actually getting an idea of shape and how atoms are connected to each other, what we call a Lewis structure. And there's actually two different ways of getting to a Lewis structure. I'm going to show you the way that I typically find works the best for me and works well for very large molecules with relatively simple bonding. For complicated bonding on small molecules, there are other approaches that do tend to work better, but yeah, that's in your textbook. I'll let you check that one out. Okay, first things first, we need some molecules. And hey, who doesn't love water? Okay, molecular formula of water is H2O. Now, that's telling us we have two hydrogens and one oxygen. Okay, now we get to figure out how to put them together. But before we do that, I actually like to convert these into their Lewis symbol. Now, you look at the periodic table and you figure out the number of valence electrons for each of these atoms. Roughly speaking, that's going to be 1 for the hydrogen, and then once you move over to carbon, he's got 4, as well as anybody below carbon. Nitrogen's going to have 5, as well as anybody below nitrogen. Oxygen, 6, as well as the rest of that group. Fluorine, 7, and its group, the halogens. And of course, the noble gases, they've got 8, and they don't actually do much of anything, so why are you doing anything with a noble gas? Okay, so back to water. We've got oxygen. That's got 6 valence electrons. So what I'm going to do is I'm going to draw an invisible box. Now, because an invisible box is kind of hard to see, I'm going to draw it in green. I'm going to draw my box around the oxygen. This box has 4 sides because oxygen's valence shell has 4 orbitals, an s and 3 p's. Now, these are not nearly as distinct as if oxygen was entirely by itself. So previously we talked about ground state electron configurations. That's really assuming that the atom in question is all by its lonesome out in the middle of nowhere. You know, nice hard vacuum. This is definitely not the case. So those orbitals are a little bit more fuzzy to talk about. But we've still got 4 orbitals in some flavor. And that's going to be each of my sides of my box. Hydrogen only has the s orbital, so I'm going to draw a one-sided box, otherwise known as a circle. Okay, now each side of the box, or all of the circle, is going to be able to hold up to 2 electrons. So I'm going to start filling them in. Now, electrons are like people. They prefer not to have a roommate if they don't have to. So we're going to fill them in such that they don't have roommates to start with. Well, each hydrogen has 1 valence electron. So, well, that's it for him. Yep, that one's done. And I'm just putting a dot to indicate the presence of an electron. Now, oxygen is going to have 6. And which side of the box does not matter at all. Put 1 dot, 2 dot, 3 dot, 4 dot. Yay, there's 4, I need 6. 5 dot, 6 dot. Now, you'll notice something. The oxygen has 2 pairs of electrons. These are what we call lone pairs, and they typically don't do much. They do chemistry. They are not unimportant, and when you draw a Lewis structure, you don't omit them. But typically, they're not going to be doing the most interesting things with respect to the Lewis structure. Oxygen also has a pair of unpaired electrons. Those 2. These electrons are going to want to find a pair. And lo and behold, I have a hydrogen with an unpaired electron and another hydrogen. Hey, we got some pairing. We can do matchmaking. So what I will do is I'll take this hydrogen and I will move it onto that oxygen. And of course, showing you the invisible boxes that we're drawing. Now, hydrogen's invisible box, its s orbital, is hybridizing with the orbitals of the atom, or of the oxygen atom, and they're now holding 2 electrons. Hey, we did it once, let's go twice. Yay, we have the beginnings of our Lewis structure. We can stop there if we want, but that's kind of messy. So typically we're going to erase those bonding pairs of electrons, these two, and replace them with a line. That line represents 2 electrons. Okay, we have the core of our water molecule, and this is a perfectly fine way of drawing it. Typically, you won't be using the green ink because that's highlighting the orbitals that we normally don't highlight. In fact, basically, we never highlight except for when pointing this out to start with. Now, let's look at a slightly more complicated molecule. This time, I have ethene C2h4. So we're going to draw this out basically the same approach. I'm going to take my constituent atoms. I've got a carbon. And you know what? I'm only going to draw the one. I know that there's 2, and I can keep track of that in my head. Likewise, I'm not going to draw all 4 hydrogens to start with. I'm just going to draw one with its 1 dot, and the carbon with its 4 dots. Remember, the carbon and most atoms are going to have S and 3 Ps, so it's an invisible bond, which this time is truly invisible. It was here. Hydrogen only has the s orbital, so, well, it's only got 1 dot anyway, so, yeah, there we go. Once again, orientation around the atom does not matter, so long as you are clearly denoting paired and unpaired electrons. Carbon doesn't have lone pairs, but it does have a good deal of unpaired electrons. Carbon, unlike most atoms, is very happy to bond with another carbon. Most atoms will prefer to bond with atoms that are not of the same element. They will, of course, make exceptions. Okay, so let's work this one out. I have 2 carbons, and as I just implied, they're probably sticking together. Okay, and I might as well just change these 2 dots into the line while I go. Now, I have an awkward situation. I have 6 places to put hydrogens, but only 4 hydrogens. I'm going to start out and I'm going to assume symmetry. It's an assumption. If I try it and it doesn't work, then hey, I'll have to try something else again. It's quite often in life, you try something, if it works, great. If not, go for it a second time. Okay, this seems legitimate. I'm going to go ahead and switch these pairs of electrons into their lines. But I still have 2 unpaired electrons. And atoms typically don't have unpaired electrons. When they do, that's known as a radical, and those are particularly unstable and generally not what you have. But notice how they are next to each other. I can pair them. I can make more than 1 bond between some atoms. Most of the time, I can go up to 3 if I have the right number of unpaired electrons. Those 2 are now a secondary bond. Okay. Instead of having what we traditionally call a single bond, I now have a double bond. And ethene has a double bond. Our next molecule is hydrogen cyanide. Not something we would want to be working with in person. But this is just ink on whiteboard, so it should be fine. Now, I'm going to do the same thing here as well. Typically speaking, when I look on the periodic table, the least electronegative element, the one that's closest to francium, is probably the one that's in the middle. Not always, but it's a fair first check to try and make my molecule doing that. If I notice, my least electronegative atom here is carbon. So I'll draw some low structures and then slap the carbon in the middle. Once again, invisible box. And then I'm going to do my hydrogen with its 1 electron, and my nitrogen. Invisible box. And 1, 2, 3, 4, 5. Okay. I have my nitrogen all set. Okay, let's start sticking things together, and let's go with the nitrogen first. I'm going to take him, I'm going to stick him over here. Okay, whoa, I've got like 5 different places I can put a hydrogen. and only one hydrogen to put. So what I'm going to do is try and make multiple bonds. So a double or even a triple bond, which is 3 bonds between 2 atoms. If I pair those 2 electrons and those 2 electrons, I can make a triple bond, and lo and behold, the hydrogen can go there. All I have to do is clean up this mess. And now I have hydrogen cyanide. We can do Lewis structures for more than just neutral molecules. We can also do them for polyatomic ions. It just takes an extra step. So in this case I have carbonate. That would be the anion in things like limestone and Tums. Well, I'm going to start by drawing my players. I have a carbon, the invisible box, and carbon's 4 valence electrons. I'm only going to start by drawing one of the oxygens because there are 3, so once I draw one, I'll know what they look like. Invisible box. 1, 2, 3, 4, 5, 6. Once again, I should point out that the orientation of the electrons on the box, it only matters that they are on the side as either a pair or an unpaired electrons. I can draw my oxygen like this. I could just as easily draw it in this fashion. Both are completely legitimate. Now, this is a polyatomic ion, specifically a polyatomic anion. Because of this, I have 2 more players, electrons. Anions have a surplus of electrons, so even if I were to draw my 3rd oxygen, I would be still missing 2 of my electrons. So, I will put a dot off to the side and another dot off to the side. This way, I know that I'm going to be adding a dot. Well, let's start sticking stuff together. I'll take an oxygen and I'll just stick it down here. Okay, I don't know. I'll take this guy and I'll stick him over there. Well, I might as well stick him over here. Okay. I still have 2 electrons in play. Those typically prefer to be on the most electronegative atom, so probably they're going to be sticking on the oxygens, not the carbon. And I have 3 oxygens, each with an unpaired electron. Not to mention that carbon's got an unpaired electron and only 2 electrons to make pairs. Hey, double bonds. I could pair up those 2. That would work. And while I'm at it, I might as well clean up all these dots because this is getting to be a mess. Okay, now all I have to do is add the 2 remaining electrons. And hey, I have a Lewis structure. Now, when we do a Lewis structure in this fashion with an ion, there's a couple of ways of doing this. Generally speaking, the best approach to indicate that this is an ion is to put square bracket, and indicate the charge. 2 minus or minus 2, depending on your preference. However, you can also indicate the charge, what we call a formal charge, and we're indicating that the extra electron is on a specific atom. In reality, it's a good deal more complicated than that, with a practice what we call as resonance structures, which will be covered in another video. If we are going for the formal charge approach, I could say minus and minus, if I wished. Typically, though, the square brackets is the best approach due to the interesting complexities of those electrons. Anions aren't the only polyatomic ions around. There are a few, although not too many, polyatomic cations. So let's show how to draw a polyatomic cation. In this case, I have ammonium, by far the most popular of the polyatomic cations. I have a nitrogen and 4 hydrogens. Obviously, I can tell the nitrogen's in the middle because the hydrogen can only have one bond. Good luck being in the middle if you can only have one connection. So it's got to have to be the nitrogen. And likewise, I'm not going to draw all 4 hydrogens, but I am going to draw one just as a template. Okay. I have the opposite problem that I've been having for a while. In this case, I have 3 places to put my hydrogen, but I have 4 hydrogens to put on. Oh wait, this is a cation. I need to do that and handle those electrons. Anions have surplus electrons. Cations have a deficit. So I like to put off to the side my remove an electron note, because I'm going to get to remove 1 electron from anywhere in this molecule that makes my life easier. Well, let's start slapping some hydrogens on. And put one there, down there, and over there. Okay, I have ammonia, NH3, but I still got 1 more pesky hydrogen, and I get to pull an electron off of it. Of course, let's clean that mess up. If I were to get rid of 1 of these electrons, then I would have an unpaired electron and a place for my hydrogen to live. So let's do it. Yay! Just a little bit of cleaning. Likewise, I could indicate formal charge and put a charge on the nitrogen because that's the one that lost the electron, but it's usually best to use square brackets. So now I have my ammonium. Okay, so there's a few molecules that are going to make life a little bit more complicated when doing this particular method of Lewis structures, but you can still do them. So one of the most obnoxious ones are those containing nitrogen and oxygen, like our nitric acid over here, HNO3. This is because the oxygens don't play too awful nicely. So let's do this Lewis structure. For starters, I've got my 3 players. The 1 hydrogen, he's never hard to deal with. The oxygens, once again, invisible, box. And 6 dots, 2 pairs, 2 unpaired electrons. And the nitrogen. Okay, these are going to go fairly straightforward to start with, but then they're going to get interesting. Okay. I have 3 oxygens. I might as well string them around the nitrogen. Okay, this is awkward. Well, I can put that hydrogen on. But now I need to clean up my electrons, and more than just doing lines. But let's do some lines first. Okay, this seems to be the obvious choice. I make a bond between these 2 oxygens. Except for oxygens generally don't prefer to attach to each other, and 3-membered rings, while they do exist, are fairly rare. Most rings are 5 or 6 atoms in size. Instead, one of these oxygens is going to do something a little bit dirty to the nitrogen. It's going to steal an electron. Yes, steal. One of these is going to move down here. This is going to impart a formal charge on that nitrogen and a formal charge on that oxygen. This is not something that atoms typically like to do, but oxygen does like its electrons. Now, 2 unpaired electrons, I can form a double bond. Yay! Don't actually have to indicate the formal charges if I don't want to. And there's no brackets because a plus and a minus cancel themselves out. So I have a neutral molecule even though there is some charge separation. Although not generally preferred. In this case, that's what you get. Our next somewhat tricky molecule is going to be sulfuric acid, H2SO4. And when you are dealing with atoms that are in period 3 and below, they've got a few more cards in their deck. They do have d orbitals in their valence shell, they're just generally not used. Note, generally. Okay, so I'm going to try and draw this doing the approach that we've taken so far, and we're going to see where things go wrong, and then we're going to realize what those d orbitals can do. Of course, I'm going to get my players involved. Invisible box, and actually I'm going to make this box visible because this box is going to change. So I'm going to start out assuming it's a square, an S and 3 P's. Foreshadow, it's not always a square. Got my oxygen? Oxygens are in group 2. They've only got an S and 3 P's. They can't be anything other than a square. And the poor hydrogen's group 1. It's just got the S. It's always a circle. Okay, let's go for the failed attempt. I'm going to put my sulfur in the middle. And I'm going to go ahead and put my electrons in this configuration just so I can make it nice and linear. I can stick an oxygen on each side, and even a hydrogen right after it. And congratulations, we have drawn the Lewis structure for H2SO2, which would be great if that was actually the molecule we're trying to draw. It's not. Oh dear. I can clean this. Forgot a dot. But that's no way to make this. So what we're going to have to do is bring those D's into play. Remember, each side of my square is an orbital. If I bring the D's into play, it's no longer going to be a square because it's going to have extra sides. In this case, I'm going to bring 2 of my 10 D's into play. I don't have to bring all of them. In this case, it's now going to be a hexagon. Okay. By the way, probably should erase this bottom part because it's going to change. I have 6 electrons and 6 sides, so everyone goes by themselves. And I can draw my sulfur in here. One from the oxygen, one from the sulfur. So again, one from the oxygen, one from the sulfur. And now I have 4 unpaired electrons. Wait, I have 2 more oxygens. I can take this oxygen and I can stack it up here. So I'll get rid of my sulfur. I can take my oxygen. Unpaired, unpaired. And I do actually like to, when I'm doing double bonds, put things at weird angles. Kind of really highlights what's going on. And in the actuality, the angles would be existing in a similar fashion for my molecules. Okay. I can do a double bond in those 2. And lo and behold, down here, I can make those into a double bond. And I'll just go ahead and get rid of these green lines. Now, I have the Lewis structure for sulfuric acid, H2SO4. The key here is that sulfur can have more than 4 bonds. Period 2 atoms can only have up to 4 bonds. Periods 3 and below can go to quite a few more bonds than simply 2 by changing, instead of having a box, having a hexagon, a pentagon, or whatever particular shape corresponds to the number of d orbitals that they brought into bear. With that said, happy drawing.